But what about m, our next quantum number? Now the textbook call it m sub l. We just call it m. It's the same thing. Okay. You know, L and M are related. In fact, we saw that M as an integer, the absolute value of M cannot exceed L. Cannot exceed L. Okay, so if L represents the quantum number for the total magnitude of the angular momentum, and M is a quantum number which never exceeds L, what does that suggest? What does that suggest? That seems to suggest that M represents some sort of component of the angular momentum, right? No wonder M cannot exceed L, which represents the total angular momentum. So let's call that component the Z component. So is it true then that M represents the Z component of the angular momentum? Is the quantum number corresponding to the Z component of the angular momentum? Is that true? Well, let's examine the following operator. I have this operator, negative IH bar partial partial phi. The if you take a look at the symbol here, H bar, besides this I is just a dimensionless number. Partial partial phi, these are all dimensionless. So this operator itself has an overall unit of angular momentum because H bar is the only dimensional quantity in there. I want to rewrite this operator, which is expressed in terms of an argument in the spherical coordinate phi. Okay, I want to re-examine it. I want to express it in terms of the more familiar x and y and z. See what we're getting from here. So express in terms of x, y, z using the chain rule. Okay, phi is a function of x, y, z. And therefore, this partial partial phi has three terms. This has to do with x, this has to do with y, this has to do with z. It's a matter of chain rule. Partial x partial phi and then partial partial x. Partial y partial phi partial partial y, and then partial z partial phi partial partial z. Okay, one can easily find what this is, and what this is. All you have to do is write down, again, the expression linking the Cartesian coordinates x, y, z to the spherical coordinates r theta phi. X equals r sine theta cosine phi. Y equals r sine theta sine phi. And z equals r cosine theta. We saw that in our previous, in the beginning of a previous lecture. It's also, you should also be familiar with it from your math class. Okay, so let's do partial x partial phi. You do this, partial x partial phi. R sine theta is the same, but cosine theta becomes what? Cosine phi becomes what? Negative sine phi, right? And that's right here, negative r sine theta sine phi. Now next, partial y partial phi, which is from here, partial y partial phi, r sine theta, you keep the same. Sine phi becomes cosine phi upon derivative. And the last one, partial z partial phi, that's just 0 because there is no phi dependency here for z, right? Okay, now, what is r sine theta sine phi anyway? That is just y. And what is r sine theta cosine phi anyway? That is just x. I'm rewriting this in terms of y, this in terms of x. And it only gets better. Take a look. This is x, which is positive. This term is y is negative, so I just switch the order. And I get x partial partial y minus y partial partial x. Now there is a negative IH bar. I'm going to sticking this negative IH bar into here and into here. So x remains and y remains. And look at what I just came up with. What is this? Do you recognize what this is? Negative IH bar partial partial y. That is the y component of what? Of the linear momentum operator. That's just py. Okay? What about this? That is just the x component of the linear momentum operator. That's px. Therefore, it is xpy minus ypx. And that is, if you're familiar with the notion of cross product, that is in fact the z component of the cross product between r and p. Okay? Between r and p, the z component is x times py minus y times px. It's just the definition of a cross product. But what is the z component of r cross p? R cross p is what? Is the angular momentum operator, right? The z component, I have Lz here. So therefore, after all this effort, what did we get? We found that this operator is in fact the operator representing the z component of the angular momentum. And is it true that our system, described with the equation of spherical harmonics, is it true that it is also an eigenstate of Lz? In other words, if I operate this thing on YLM, will I get a constant times YLM itself? Let's see that. It's very easy to do. Negative IH bar partial phi YLM. I'm only concerned about phi, the derivative. Therefore, the theta part of the YLM, which is the hard part, is just a constant. It never changes. The phi part is very simple. E to the im phi. Okay, it's e to the im phi. There is a constant demolition. There is a normalization constant in front of it. I don't really care. So I rewrite YLM in terms of this product, and this theta part of the equation, I just take it out because there's nothing. It has nothing to do with partial phi. And then when I take a derivative, okay, e to the im phi, then partial phi, what do I get? I get im times itself, right? Im times negative IH bar. What is that? Im times negative I H bar. That is just mh bar. Mh bar times the product, which is YLM. So you see, indeed, this operator, this LZ operator, acting on YLM, produces a constant times YLM itself by definition of eigenequation. This is an eigenequation. This is the eigenequation for this operator LZ, and therefore YLM indeed is an eigenstate of LZ as well, not just L squared, but LZ as well. And here we have the eigenvalue of LZ. This is the Z component of the angular momentum. No wonder M cannot exceed L, because otherwise the Z component can be greater than the total angular moment itself, which would make no sense. Okay, so you see here, LZ equals mh bar. So this YLM is an eigenfunction of L squared. It is also an eigenfunction of LZ. Therefore, it is a simultaneous eigenstate. It represents a simultaneous eigenstate of both the magnitude of the angular momentum as well as the Z component of the angular momentum. So we can plot in the XYZ space, we can plot L and LZ. Here is the angular momentum vector L, and here is the Z component. The angle between them is theta. Now we know that the magnitude of L, this vector, is the square root of L times L plus 1 h bar, and the magnitude of LZ is mh bar. In fact, m can also be negative, so this thing can point downwards if L goes like that. We notice that m and L are just quantum numbers. They are discrete values. They are 1, 2, 3, 4, and so on, or negative, negative, whatever. They cannot be just any continuous value. And that tells me that the angle between them is not just arbitrary. We can calculate this angle, cosine theta, as this length over that length. That's LZ over L. So we have this, right? Look at this. M divided by L times L plus 1. Again, M and L are integers, which means cosine theta cannot just be an arbitrary value. It must make sure that cosine theta equals to this expression. So what that tells us? It tells us that when you project the angular moment onto the z-axis, an arbitrary z-axis, it's going to make an angle. Okay, the angular moment is going to make an angle theta with the z-axis, and this angle theta cannot be anything. It must satisfy a certain set of values. In fact, however many m you have, then however many angle theta you have. For every L, there are 2L plus 1 different values of m. So therefore, theta has 2L plus 1 different values. The angular moment operator, the angular moment vector can only point at one of these 2L plus 1 values. It cannot point in any direction. It appears that even the space is quantized. It only allows you certain values to point at, and we have an interesting term for that. We call it space quantization. Okay, again, there are only 2L plus 1 different possible value for theta, each representing a different m value. We call it space quantization. Now, also you notice that as LZ get greater and greater for the same value of magnitude L, theta gets smaller and smaller, right? Normally, for the angular momentum, it is possible for the angular momentum to be totally on the z-axis, therefore theta can be 0. Certainly in classical case, there is nothing against that, right? There is nothing that tells you that you cannot point the angular momentum on the z-axis necessarily. But here we cannot do that. You see, because even the minimum value of the cosine function, of the cosine. Even take theta minimum, the cosine value of that theta minimum, which corresponds to the largest LZ magnitude divided by the magnitude of L. What is that equal to? M maximum over square root of L times L plus 1. Here you see the subtle difference between L squared and L times L minus 1. I'm sorry, L times L plus 1. If you ignore that 1 here, then you get L squared, square root, that L over L, that's 1, which means L can totally lie on the z-axis. But interestingly enough, the magnitude of L is not equal to L times h bar, but the square root of L times L plus 1 h bar. Now, we got that expression in the last lecture. Even though we didn't quite do it step by step, I told you it was because we had to satisfy the boundary condition for the theta function, right? The theta part of the wave function, which is the associated Legendre polynomial. If we do not choose two consecutive, the product of two consecutive integers, then this function will diverge at theta equal to 0 and theta equal to pi, so we are forced to do that. But does it really carry any implicit message? Yes, it does. In the case of angular momentum, it tells me that it is impossible to put this entire angular momentum vector on a fixed z-axis, because this angle theta, even at the minimum value, is never equal to 1. And the cosine theta is never equal to 1, which means theta minimum is never equal to 0. It's less than 1, you see here. Why is that important? Because let's consider if that were not the case, okay? If you do not have that 1 here, so that cosine theta minimum equals 1, so theta minimum equals 0, then this L, again, only has a z component. It's completely on the z-axis. So what is Lx? What is Ly? They're both equal to 0, right? So when you try to measure the x and y components of L, you're going to get 0 and 0 all the time. And when you measure the z component, you only get one value, which is mh bar. It's m equals L in this case. Okay, what does that tell us? It tells us that you are now able to measure all the three components of L, of the angular momentum L. Lx, Ly, and Lz. The first two, Lx and Ly, both equal to 0. No matter how many times you measure it, you get 0. And the last one, Lz, you just get Lh bar all the time. So you have just found a simultaneous eigenstate for all the three components of the angular momentum operator, Lx, Ly, and Lz. But you know, that is just not possible. Why is that? Because the angular momentum, the three components in angular momentum, Lx and Ly and Lz, in operator form, they do not commute with each other. Okay, we introduced that last time. In the previous lecture, in fact, in the previous chapter, in fact, we found, well, actually, we wrote it down. We didn't really prove it, but it can be shown that Lx, Ly is not equal to 0. The commutator is equal to IH bar Lz. It's not equal to 0. And Lz, Lx, if you did that, you get IH bar Ly and so on. They do not commute with each other, even though each one commutes with L squared. Okay, Lz commutes with L squared, so therefore you can find L squared and Lz accurately simultaneously. But you cannot find all three components, Lx, Ly, Lz, simultaneously with accuracy. So therefore, this angle can never be actually 0 degrees. If that happened, like I just said, all three components will be exactly known. Two of them are 0. The last one is LH bar, which has violated the Heisenberg uncertainty principle. So this is a self-consistent theory. This L plus 1 actually plays an active role. Without that, quantum mechanics would not be self-consistent, because you would have just violated the Heisenberg uncertainty principle for the components of Lx, Ly, and Lz. We also notice that as L becomes really large, the difference between L and L plus 1 is negligibly small, and therefore this L times L plus 1 business is just basically the same as L squared. You take the square root, the angle theta minimum will gradually approach 0. And that makes perfect sense, because again, when L becomes very large, we're looking at a very large amount of angular momentum. This goes back to classical physics. Of course, in classical physics, there's no such thing as non-commutation of operators, that sort of thing. And therefore, as L becomes very large, you should go back to classical physics where the minimum angle is permitted to be 0. All right, let's continue to look at an example of the space quantization using L equals 2, a very common value. Oh, by the way, L equal to 0. When L equal to 0, the cosine angle can be equal to 1, and then indeed there is the minimum angle is 0. But you know, when L equal to 0, we don't even have to worry about angular. It doesn't exist. Okay, we have an operator with we have a quantity L with 0 amplitude. It does not even exist, and therefore there's nothing to worry about. Now, space quantization for L equal to 2. Here is an example. For L equal to 2, 2L plus 1, which is 2 times 2 plus 1. There are 5 different values. 1, 2, 3, 4, 5. Each corresponding to a unique LZ value. So LZ equals 2H bar, 1H bar, 0, negative H bar, and negative 2H bar. But the square root of L, the magnitude, is not equal to 5H bar. It's not equal to 2H bar. Rather, it's the square root of 6 times H bar. Okay, it's 2 times 3 square root, not 2 times 2. So, again, here's the minimum angle. In this case, the minimum angle is not 0, as you can see here. Okay, it's not 0. This arrow is only the z component. It's not the vector itself. The vector itself for L, 1, 2, 3, 4, 5, only 5 possibilities. And so this is what's happening to the z component. The z component is fixed. So is the total magnitude of L. But what about x and y components of the angular momentum? No, you know they are not fixed, right? They're not fixed. So what are they doing? When you measure it, every time you measure LZ, you will get the same value. But every time you measure L and XY, you will get a different value. That is because the vector L, this vector here, actually turns around and around and around about the z-axis. As it turns around the z-axis, making a cone, you know that the component of the z never changes for each cone, right? No matter where you are. But as the tip goes around and around, every time you measure L and X and Y, you are going to get just a random value. You don't know what it is. Because you project this cone onto the XY axis, XY plane, you never know where the shadow comes in. So this is the behavior of the quantity angular momentum. It turns around in the shape of a cone like this, keeping LZ fixed and L fixed, but you cannot keep LX and LY fixed due to the example of due to the application of the Heisenberg uncertainty principle. So after all this talk about the z component of the angular momentum, which has to do with m, we still haven't named m, right? You know, L was called orbital angular momentum, and m, we call it the magnetic quantum number. Magnetic quantum number instead of the orbital quantum number. Why don't we call it z component of the angular momentum quantum number? Well, that's cumbersome, right? But is there a reason we call it a magnetic quantum number? Yes, there is. Because if you just look at an isolated hydrogen atom, okay, and then you find from our calculation in the previous lecture, you find that n is the only quantum number which determines energy. The energy levels degenerate for different values of L and for different values of M. However, if you put this atom in a magnetic field, in an external magnetic field, then you find that energy states with different M values, with different values of M, we assume different energy values. In other words, the degeneracy for different M will be lifted. Lifted means it is no longer degenerate about different values of M. Lifted. So let's see what happens when we put it in a magnetic field. Okay. You will then encounter an additional term in the potential energy, U magnetic, equal to negative mu dot B. Now remember from physics 1C, a magnetic dipole exposed to a magnetic field B will have a additional interacting potential of negative mu dot B, mu being the magnetic dipole moment, right? Here is the magnetic dipole moment due to the orbital motion. You have a charge, actually negative E, right? Negative E, that's the charge of the electron. The electron goes in a circle, whatever orbital like this. Let's say it's a circle for simplicity. And then it produces a magnetic dipole. This dipole exposed to a B field, which is along the z-axis. Okay, we call the direction of B, we call it the z-axis. will then interact, the dipole will then interact with that B field, and here is the additional term in the potential energy. And since B is along the Z axis, when I take this dot product, mu L becomes mu Z, the Z component. But mu L is related to L. Here is the magnetic dipole moment due to the orbital motion of this electron. Here is its angular momentum. They are related to each other. In fact, they're proportional to each other. In fact, it makes sense. The faster you turn, the greater the current you produce, so therefore the greater mu. Yes. Let's see here. Mu L, by definition, from physics 1C, we know it's I times A. What's I? I is the current produced. What's A? A is the area enclosed. It has a direction, and that direction is defined with the right-hand rule, which means suppose the current goes this way. Okay, suppose the current goes this way. Then you're going to use the right hand to wrap around the direction of current, and here is the line perpendicular to it, and that is the positive direction of the area A. Okay, so perpendicular to the plane which contains the orbital motion, using the right-hand rule, following the direction of the current. So I times A. Now let's do that. In this case, the electron being negative charge goes this way. Goes this way. Therefore, the current it produces goes that way, right? Goes that way. So therefore, if I use the right-hand rule, I find that here is the positive direction of Z, not the other way around. So, so you have the mu L, negative E over T. Negative E over T. In fact, I should put a positive E over T this time, because the overall direction of mu L is already determined to be along the positive Z direction, so it's positive. This is here is the unit vector along Z direction. I usually call it K, but I don't want to use K here because it sort of confuses with some other notations, such as the constant in front of the Coulomb potential. So let me just temporarily call it Z. Okay, it represents this again, the unit vector along the Z direction. The current produced by a single charge is the charge itself divided by the time it takes for this charge to complete one turn. Because every time another t comes by, t is the time it takes to complete one turn, another charge E goes through. So charge divided by the time it takes for that charge to pass through is E over T. That's by definition the current. A has the magnitude of pi r squared, and the direction is Z. Okay, direction is Z. Now let's continue. I'm going to rewrite this in terms of E over 2, and then 2 pi r over T. I'm taking a factor of a 2 pi r, so 2 and 2 cancels, and here's r squared, here's r squared. Okay. What's the significance of 2 pi r over T? That's circumference over the time it takes to complete it. That's the speed, v, isn't it? So it's negative 1/2, in fact positive. Okay, because I shouldn't use a negative sign here. Positive. All this becomes positive until the last minute, you'll see. Okay. 1/2 E V R Z. Now you take a closer look, you'll find here is V and here is R. This is very close to what? To expression of the angular momentum, with the exception of the mass of the electron m. So I'm going to multiply here with a factor of m and divide it by same m. This is indeed what? The angular momentum magnitude, right? MVR. Now, 1/2 E over m. What is the direction of the angular momentum? So the angular momentum, it doesn't care whether the charge is positive or negative. It follows the direction of v, okay? So if v is like that, then the angular momentum points downwards, right? Along the negative z direction. So therefore, I have a positive mvrz. Therefore, what this whole thing is, that is opposite to the angular momentum. So this is where I should use a negative sign. Sorry. Okay, a negative sign. Because z points this way along b direction, but the angular momentum points that way. So that way, and negative. Okay, now what I did from here to there was I divided the angular momentum operator by h bar and multiply here by h bar. Why did I want to do that? It's because the magnitude of the angular momentum is L times L plus 1 times h bar. L is just a quantum number, so L times L plus 1 h bar. L times L plus 1 is square root. The order of magnitude is about unity, about 1. The magnitude, the order of magnitude for the angular momentum in quantum physics is actually h bar. So I'm going to divide this off by h bar. So this whole thing here has roughly a magnitude, order of magnitude of 1, okay? And therefore, the order of magnitude of mu L is actually determined by this thing in front of it, E h bar over 2m. E is the mass of the electron, h bar over 2m. M is the I'm sorry, E is the charge of the electron, and M is the mass of the electron. And this combination, EH bar over 2M, again, it represents roughly the order of magnitude of the magnetic dipole moment of the electron due to its orbital motion. We call it the Bohr magneton. The Bohr magneton has a unit of energy divided by that of the magnetic field, so it's joule over Tesla, but joule again is too large a unit. We can convert that to EV, and if you did that, you get EV per Tesla, and here is the numerical value of the Bohr magneton, 5.788 times 10 to the negative 5 EV per Tesla. And you know what that means? It means that if I put this electron, which is part of the atom, in a 1 Tesla field, okay, expose it to the magnetic field of about 1 Tesla, what kind of interacting potential are we talking about? What is the order of magnitude? Well, the order of magnitude would be equal to the order of magnitude of mu z times the order of magnitude of b. Mu z and mu l, they're about the same, and the order of magnitude is mu b. So basically, it's mu b times b, and mu b is about 6 times 10 to the negative 5. Then times b is about 1 Tesla, and you're looking at this much. You get about 10 to the negative 4 EV as the order of magnitude of the magnetic interaction. So this is useful because it gives us the order of magnitude estimation. Okay, and to complete this story, we need to know what mu L is. You plug the mu L into here, you will get the a more detailed expression for the U magnet. Okay, the magnetic interacting potential. Negative mu b L. See this thing here? I just plug in the expression for mu L here. Negative mu b, and then L dot b divided by h bar. L dot b is again negative mu b Lz, and then divided by h bar. But Lz itself has an eigenvalue of mh bar. Okay, so m and h bar divided by h bar. This is what you get. This is the expression for the potential energy difference when you expose this atom to a magnetic field. You see, indeed, for different m values, you're going to get different values of U magnet. And that is important because it tells us that this m really indicates the energy difference when you put this atom in a magnetic field. No wonder we call this m the magnetic quantum number. Again, different m values usually produce the same exact energy. You don't notice any difference. But you put it in a magnetic field, different m values will yield a different add-on of energy. And so when we expose this atom to a magnetic field, this is what we get. The spectral lines will then split according to different values of m. However number of values of m you have, however new lines you're going to get. Okay, this is L equal to 0. So this is the lowest, this is ground state. The ground state is L equal to 0. For L equal to 0, there is only one m, okay? There is only one m, which is 0, and therefore, you don't have any splitting. You don't have any splitting. You put it in the magnetic field, nothing happens. It's still the same. But if you put it in if the atom is in an n equal to 2 and L equal to 1 state, then L equal to 1 corresponds to 3 different values of m, right? Negative 1, 0, and positive 1. You see, as a result, the energy, this one line is now split into 3 lines. Here, m equal to 0, there is no change from here to there. Because the change equals to, how much? You see, the change equals to negative times mu b times m, right? But for m equal to negative 1 and positive 1, now you see a difference, right? It goes down by mu b times b, and it goes up by mu b times b, depending on what the value of m is. So it splits 2L plus 1 different ways. This is the number of possible values for m. Each m gives you a different energy. So it's going to split into odd number of spectral lines. That odd number is determined by L. It's total 2L plus 1 spectral lines. So this single spectral line is now split into 3 spectral lines from this state to that state. This is called the Zeeman effect. That's basically what happens. You put an atom in a magnetic field. You see splitting of spectral lines based on different m value.